хвилин, я вмикаю ефір.
Hello, dear colleagues and friends. I am glad to welcome you on the fourth international conference, Design, Simulation, Manufacturing, the Innovation Exchange in Lviv. My name is Oleg Zabolotny, Lutsk National Technical University. Now we have started the second session, Manufacturing and Engineering 1, and today we will see 5 presentations of works our colleagues submitted to this conference. All speakers will have up to 8 minutes for your presentation and about 2 minutes for answer the questions. And now I'm glad to invite first speaker, Dmitro Lesik, and his international team from Spain and National Technical University of Ukraine, Igor Sikorsky, Kyiv Polytechnic Institute, Ukraine. This presentation were characteristic of carbon and tool steel hardened by combined laser ultrasonic surface treatment. Dmitro Lesik, Kyiv, National Technical University of Ukraine.
Hello, I am here. Unfortunately, I could not switch on camera. I don't know. I got a notification didn't switch on camera. Do you hear me? It's great. Hello, do you hear me or no? I'm sorry.
Почекаємо. Хай під'єднується. Архат? Де Архат?
Зараз. Раз.
Первый.
Do you hear me? Lessig Dmitro here.
Good day.
Hello, Dmitro. Now your presentation. You have started.
My name Roman Arhat.
Thank you.
Article name the contact pressure in drawing parts without clamping the workpiece flange. Please, slide number 2. Drawing of asymmetric parts is characterized not only by the loss of flange part stability, but also by the deformation localization in the zone of the transition of the wall to the bottom and the destruction of the workpiece at a given location. The drawing down without workpiece flange pressing is limited by the formation of workpiece and compression part, and the bottom separation can occur if the process workpiece retraction into the die body hole continues, ignoring the faults of the flange. Next slide, number 3. It is possible to extend the interval of non-collet foraging by increasing the resistance of the flange, loss of stability, or by increasing tensile stresses at the initial stage of deformation. The blank flange practically does not contact with the surface of the die body. Since when the punch is lowered, the flange portion rises above the die body and form a conical surface with an angle A alpha at the apex. Therefore, the contact of the workpiece with the die body occurs along its toroidal surface with a certain rounded radius. The existing analytical dependence for calculation stresses at the radius of the curvature do not fully take into account all the minute details and technological factors of the drawing process, and their accuracy is not satisfactory. The presence of defined formal dependencies describing the distribution of stresses on the drawing edge of the matrix, taking into account friction, bending moment, contact pressure, blank thickness, and other, will make it possible to expand the range of drawing products without pressing the flange and reduce rejects to a minimum. Next slide, 4. To determine the contact stresses, we start from the equilibrium equations for the torus, but taking into account the surface load. We take into account the fact that the deformation is asymmetric, and therefore the terms of the system containing delta phi. The basic calculation equations are shown on slide number 5. The first and second terms are of the some order of smallness and can be neglected with an arrow up to the third decimal place. Then the surface load is the following equation number 7 at the slide 7. Slide 6, sorry. Slide 6. Thus, an expression has been developed for calculating the surface contact pressure during the drawing down and cylindrical workpiece, which make it possible to take friction stresses into the rounded radius of the die body, and also of calculated drawing force. The dependence obtained differs from the existing ones by its simplicity and visibility, and can be used at the preliminary stage of choosing equipment for foraging. To verify the obtained dependence by the determination of contact pressure, experiments have been carried out to measure the load cell deformation case by frictional force. Slide number 7. The experimental data are used to verify the adequacy of the mathematical model of the distribution of contact pressure on the die body around its radius when drawing without collet. Next slide, number 8. In table, the numerator of the volumes of the diameter, the draw ratio, the stroke of the punch, the value of the contact pressure is related to the drawing option with the rounding radius of the die body RM 4 millimeter. In the denomination, it's the same for RM 1.5 millimeter. Delta and percent is a deviation of the experimental data from the theoretical ones. Next slide. Next slide, number 9. The result of experimental studies shows that the greatest condensance with theory is 6.7%, and the greatest discrepancy in calculation is up to 87% for steel. The discrepancy between the result of experiment studies and calculated data in general can be explained by the imperfection of the mathematical model when all factors of constructive and technological nature are not taken into account, as well as hardening of the metal during plastic deformation. In particular, the greatest discrepancy is the result of observed with drawing blanks of steel and copper with rounded radius of the die body of 4 millimeter, which is obviously connected with the shows of the rounded radius of the die body. For the metal thickness used in the experiments, it is science is goes beyond the recommendation of the technical literature that is around 8, 10. This pattern does not reflect the analytical relationship, but gives a more accurate match of the data. Therefore, the completion of the dependencies obvious, but in the existing format, it can be used of calculation the drawing process with the rational geometry of the tool. Thank you for your attention.
Thank you, Roman. Dear colleagues, maybe you have a question, please. You're welcome.
Professor Dobrotovsky, I don't understand what laser, kind laser use you in your experiment. Where is laser? And where is ultrasonic in your model?
In this model, laser not.
No, in your abstract, we use combined laser ultrasonic method. Maybe
No,
I don't understand.
This method of asymmetric drawing parts without clamping of workpiece plane.
Repeat, please. I don't understand.
This method determination of contact pressures when drawing a part without clamping the workpiece flange.
I understand. Они не использовали ничего.
Thank you. You don't use this method. Yes. Maybe you have any questions? No. Thank you very much, Roman. Thank you for your presentation. Waiting you next year in this conference.
Okay. Thank you.
Have a good day. And now I invite to presentation Oleg Akimov from National Technical. Oleg Akimov, yes?
I am ready. I am ready.
From National Technical University, Kharkiv Polytechnic Institute, Ukraine.
Thank you. The first slide. First. The main themes of our research is ensuring the technological parameters of cast block crankcase of automobiles diesel engine. On this slide, you can see introduction and major challenges. All processes, computer-aided design, technological preparation, and production of cast engine part in integral parts of systematic approach inherent the ALF technology. Please, next slide. The main aim and research task. Modern design in foundry production includes development of 3D model of a part casting system and equipment. And also, the processes that take place must be consistent with practical methods that allow to get high quality parts with high performance characteristics. The purpose of this work is to analyze the quality of cast block crankcase using an universal technology of complex computer integrated design of cast parts of internal combustion engines using engineering modeling of thermal and hydrodynamic parameters of casting. Computer modeling of casting processing occurring in the manufacture of cast part of the block crankcase is performed to identify the places of formation of defects, determine their location and estimated size, as well as for subsequent analysis of the fast transition process when cooling the casting of the block crankcase in form. The next slide, please. To perform this task, the following sequence of stage was proposed according to the methods of computer modeling of thermal and hydrodynamic casting processes. Determination of initial conditions, development of 3D casting models based a diesel block crankcase with technological heating filling system, computer integrated modeling of foundry processes for the production of cast block crankcase, analysis of the results of computer simulation, analysis of the nature of filling the mold with metal and the location of casting defects. Will you next slide? On this slide, we can see 3D models of cast crankcase of diesel, final volume model of casting in the chill with the displayed cells. Slide, please. The boundary conditions and initial data. 3D models of block crankcase casting technological heating system was created in the works. The heating feeding system created is a tapering tape system that ensures by its design the correct and gradual filling of the form with metal in order to avoid the ingress or slack inclusions into the cavity. The boundary conditions and initial data for modeling according to the following sequence were set. 3D import and create infinity difference model, the purpose of the material for casting and tooling, as well as separation coating applied to the surface of the tooling. Setting the initial temperature and the melt of and process equipment. setting the total production cycle time for single casting. Will you, the next slide? The assignment of boundary conditions. Block casting, you can see block crankcase casting material. Material of technology equipment, steel 20, gray cast iron 20. The forming parts of the chill are coated with the chill paint with thickness of 0.2 millimeters, which has a thermal conductivity to prevent moisture from entering the forming surface and high temperature difference when pouring the melt. The process equipment was preheated to temperature, you can see. The melt temperature before pouring into the mold was 83 Kelvin. The next slide, please. On this slide, we can see results. The obtained results of computer engineering modeling are presented graphically in the form of filling the mold with a melt. The reaction of crystallization during cooling, transition from the liquid to the solid phase, and displaying the location of gas-shrink labeled defects. The type of filling in the forms plays an important role in creating favorable conditions for directed crystallization. The velocity of melt movement when filling the mold in separate parts did not exceed the critical values. With smooth filling the mold without splashes and with small vortices according to the requirements. Will you, next slide. The results of our computer simulation analysis. Passing through the elements of the gating system, the melt does not acquire the turbulent character of movement. The movement filled with exceeded critical speed. The analysis of the results of computer integrated simulation of the cooling process of the part is the technical mold was carried out in accordance with the parameters. Transition from the liquid to the solid phase during cooling of the part in the form has shrinkable defects impressed by the Nayama criterion. Will the next slide. On this slide, we can see transition from the liquid to the solid phase during the cooling of the part in the chip. The next slide, please. In this slide, we can see locations of gas shrinkable defects according to the Nayama criterion. The next slide, please. Analysis of the location of defects shows the most prone to shrinkable place are at the cases of the cylinder, the upper plane of the front part of the block in the place of attachment under the heat, erases of bosses of the size of block. Modeled defects allow us to make a forecast that the cast product may be defective by 5 to 6%. As a result of computer engineering modeling of the thermal hydrodynamic processes of block crankcase casting, it follows that gas shrinkable defects can be stress concentrators in the structural elements of the part and therefore can affect the strange characteristic during operation. Will you, the next. For the future, you can see conclusions, and for the future research, the results of this research allowed us to form boundary and initial conditions for modeling of stress-strain state of the block crankcase in the places where gas porosity is formed. Further development of the above studies will be carried out for casting on new types configurations, other casting technologies, new synthesizers, alloys. The next slide. Thank you for your attention.
Thank you, Oleg, for interesting work. Dear colleagues, maybe you have questions, please. Have you a question in chat? No? Thank you, Oleg.
Thank you for you.
And now I want to invite to presentation Dmytro Lesik, National Technical University of Ukraine, Igor Sikorsky, Kyiv Polytechnic Institute.
So thank you very much. I'm sorry for the inconvenience. So dear participants,
Yes, I see. You can start, Dmytro, your presentation. You have about 7 minutes.
yes, but I cannot see my presentation. Where? So could you open my presentation or give me instruction? Because I don't see.
You can start.
No, I understand you. Thank you very much. But where my presentation? I don't see it. Maybe I open my presentation laptop. Okay, maybe next, because I cannot understand where I can open my presentation in your program. Да, please, where? Да, я чую, тільки я не можу зрозуміти. Так. Да. explain more? Да-да, знайшов потім. Угу. Да-да. Да. Фу. Okay, thank you very much. So my name is Dmitro Lesik. I work at the Department Laser System and Physical Technologies at the National Technical University of Ukraine, University Kyiv Polytechnic Institute. In particular, I'm going to present a study on the topic where characteristic of carbon and tool steels hardened by the combined laser ultrasonic treatment. So currently the problem of extending life of metal components is very relevant in both economic and resource-saving aspects. One of the most promising directions for extending the life of metal parts is the improvement of technology processes by highly concentrated sources such as laser beam or electron beam and plasma arc. The application of the surface heat treatments combined with mechanical surface treatments may significantly increase in the wear and corrosion resistance of the structural and tool steels. Therefore, today we are present you a new techniques where we combine laser heat treatments with ultrasonic impact treatment. Next slide, please. And especially in this work, we compare the surface properties of the carbon and tool steels hardened by laser heat treatment, ultrasonic impact treatment, and combined laser ultrasonic treatments. It should be also noted particular attention is paid to the study of the wear behavior under oil lubricated conditions in the quasi-static and dynamic loads. Next slide, please. The chemical composition and mechanical properties of the studied steel are given on this slide. Next slide, please. Laser heat treatment of specimens was conducted using 1 kilowatt fiber laser, high frequency scanning optics, and mirroring center with numerical control. It should be also noted during the laser heat treatment, a PID controller was implemented to ensure a control surface temperature in this laser spot. The optimized laser parameters is presented on this slide. Next slide, please. The ultrasonic impact treatment of the specimens was conducted using a special multi-pin impact head with 7 pins. The ultrasonic vibration system was mounted on milling machine with numerical control and pressed to the specimens with 30 Newton. The scheme of the ultrasonic treatments you can see on this slide. Also, the optimized ultrasonic parameters is presented in table. Next slide, please. Then the hardness specimens were tested in both quasi-static and dynamic loading wear conditions. The quasi-static tests were performed by reciprocating sliding of the hard metal spherical contrabody with a frequency of 1 Hz along the track of 4 millimeters at constant load of 30 Newton. In the dynamic conditions, the wear tests were implemented with additional dynamic load applied in sinusoidal way with a frequency of 25 Hz. Next slide, please. The typical surface texture and profiles after applied surface modification methods you can see on this slide on the left. Regardless of the initial surface roughness, combined treatment provides the average surface roughness about 0.25 micrometers due to a specific micro-relief formation. At the same time, the surface hardness was increased by more than twice after combined treatment. This is because the severe ultrasonic surface deformation caused a refinement of martensitic grains in the near surface layer formed by laser transformation hardening process. Next slide, please. As a consequence, the layered microstructure is formed after combined treatment. The laser ultrasonic affected zone, laser hardened zone, transition zone, and heat affected zone in the studied medium carbon steel is presented on this slide. Compared to the other surface hardening method applied in this work, the combined process provides the highest values of lattice microstrain and the lowest grain size. In particular, the grain size was about 25 nanometers after combined treatment. Next slide, please. There were tracks in the quasi-static and dynamic conditions for the initial and after the applied surface treatment are presented on this slide in the second slide. This study was made by using laser microscopy. It can be seen that the width and depth of worn tracks indicated by arrows you can see are larger after the dynamic wear test due to the application of additional alternative components of load. Next slide, please. Here we should say you can see after laser heat treatment you can see the oxide films which was eliminated by ultrasonic treatment after laser heat treatment. Next slide, please. And here we can see the results, especially wear loss and friction force registered after the short term and long term for the initial specimens and treated by used surface modification treatments. It's clear that the format fine-graded microstatic structure coupled with high hardness and low roughness provide the smallest were lost values. For instance, the rate of losses of carbon and tuned steel after long-term tests in the dynamic condition were decreased by 84% and 75% respectively after combined process. Next slide, please. So based on the above mentioned results, the combined laser ultrasonic treatment can be recommended for surface modification of structural or tool steels to increase both wear resistance and corrosion. Of course, our next step is to get more deeper hardening depths. Thank you very much for your attention, and especially I'm sorry for inconvenience during this.
Thank you, Dmitro. Thank you for your interesting work. And maybe you have questions. You're welcome.
First, I sorry about my question to all. One question: what kind of laser use work? Is it pulse laser or not?
No, it's, thank you very much for your question. It was fiber laser with continuous wave mode.
Continuous, okay. What length value is in this laser?
1.06 micrometers.
Oh, thank you very much.
Thank you.
Thank you, Dmitro. Have a question?
I'm sorry, one again.
Thank you very much. Waiting you next year on this conference. And next presentation from Lutsk National Technical University. I invite Boris Predalny with presentation the dynamic model of the automatic lamping mechanism with a rotating input link. Yes.
Yep, I'm ready. Where is my presentation? Are you hearing me?
Yes.
Unfortunately, I can see my presentation. The same question. I have moved together in regime razum in Skype. Yep, I've done it. What I haven't this possibility. Yep, slowly. I can start because I have my own presentation. I can start, okay. Good afternoon, dear participants. My name is Boris Predalny. I work as a teacher at Lutsk Technical University. And in this report, I want to talk about clamping mechanism. Probably it's a strange device for some people, but clamping mechanisms that, especially that mechanisms that are using for fixation some changeable elements on a spindle units. That is not some simple mechanism because as you know, the machining of workpiece require relative motion between workpieces and tools. That is obviously okay, and as well that in this case the force interaction appear. So the productivity and quality of machining is directly depend on the characteristic of such this shaping forming elements. And to provide transfer some forces from a spindle to workpiece or to instrument, we should to use clamping mechanism. And in a case of classic metal work machines, this transfer provided by using friction forces. So the maximum cutting forces, cutting modes, is strictly restricted by value of that friction forces. Because in other case, if the forces of interaction, so-called cutting forces, if they are bigger than friction forces, in this case we get sliding the workpiece or instrument related to the spindle. In this okay, in the third slide, you can see that some disadvantages which was revealed in result of my research, and it was all types of clamping mechanism was figuratively divided on 4 main types, divided according to the form of so-called force fluid, and was find it out so-called main disadvantages. And one of the promising construction design of this mechanism is that design which are based on a geometrical locking, so-called zastipka in Ukraine, and based on a self-breaking. Special terms, I'm not sure that we can translate properly in English. And it is the most promising because they provide the possibility to retain the clamping state during machining without supplying energy from outer energy sources. And that's reliable fiction because it doesn't depend from the stable work of electrical network or hydraulical network, something like this. But of course, there is some problem that related to the different to deviation size of a clamping surface. And one of the promising construction of clamping mechanism is the mechanism is self-locking by using friction forces. And on the slide 4, you can see the construction of that. Actually, it's just actuator of clamping mechanism, because it's one of the most important part of clamping mechanism, where we can see that there is a rotor of electrical motor and stator. In result of electromagnetic interaction between these elements, we get rotation of the rotor, which is located on a through its surface, and in the result of this rotation, it get axial movement. And as you can see, in this case, the input energy is not some mechanical hydraulical interactions that can cause to some distortion, deterioration, spindle stability. And of course, it was chosen like a simple for estimating some dynamic characteristic. And on the next slide, you can see that in scheme where interaction between the clamping mechanism and other subsystems of metalworking machine is presented. That is presented in the form of some simple elements for which the masses and inertial moment is reduced, so called prevailing momentum mass. And next, in slide number 6, I guess, we can see the dynamic model where is shown the gaps, the elements with some reduced rigidity and damping elements, and the type of interaction among them. In the result of this research, we get some complex of the next slides. We get some complex of mathematical dependencies which can be used like target function, or which can be used like a complex of restriction when we try to create especially highly performance equipment, because clamping, as I said, clamping mechanism provide the value of clamping forces for retaining the workpieces or tools, and on the other hand, clamping mechanism actually that is big part of a spindle unit. Therefore, it has big influence on the dynamic characteristic of the spindle unit. Of course, in this case, we can get a high frequency of rotation of the spindle, and that is also a problem. That is acts like deterioration of productivity, or rather a quality of suffer which you can get, because to get some smooth suffer, some suffer with suffers with high characteristics, we need to apply high frequently rotation of spindle. And as you see, the clamping mechanism can affect all this direction, like clamping forces that allow us to get some cutting mode and speed the rotation of the spindle, and we can find some to create some highly developed clamping mechanism. We should find something like compromise between this geometric and mass parameters of the clamping mechanism, because if you create just a clamping mechanism with the possibility to create some big clamping force, it can affect the dynamic characteristic of the spindle, and also restrict our ability to get some high frequency of rotation of the spindle. And in the slide at the end, we can see something like recommendation. It's a result of my research, and by using this recommendation, we can obtain some more optimal, not design but structure. We call it structura of a clamping mechanism and spindle unit at all. I guess that's enough for delivering my idea about this research. That's all.
Thank you very much, Boris. Dear colleagues, maybe you have a question to Boris Predalny. Thank you very much, Boris, for your interesting work and good results, and wait to you next year. Have a nice day. Thank you.
Thank you. I hope it was really interesting for you.
And the last presentation in our session, I invite Oksana Titarenko from National Academy of National Guard of Ukraine, with her colleagues from National Technical University, Kharkiv Polytechnic Institute. You're welcome, Oksana.
Good day, dear participants, dear colleagues. Can you hear me? Hello?
Yes, we hear you.
Thank you. Dear colleagues, I would like to present our result from research in the field of diamond spark printing. And you can see at the title, we have tried to machine hard alloys using solid lubricants. As you know, grinding is one of the most energy consumption and resource consumption processes at the manufacturing. And we have a lot of big troubles with such energy consumptions. At the last slide, please, you can see related and significant influences. Next slide, please. As well of the process, we can see here energy consumption, process temperatures on the tool, like toolware and thermal load on the piece, material structure and surface roughnesses, and machine systems. And another big source of influence in all grinding process, cutting fluids. We could use cutting fluids to dissipate heat, volume of heat from our cutting zone, and reduce friction. As you know, next slide, please. Here we have a big amount of consumptions, different kinds of mineral oil based cooling mineral fluids and water based. And you can see on this slide also peak consumption with prediction till 2027. Only at the USA in billion, a lot of a big amount till 2005, and it has a significant negative effects as well on human health and also on the environment. That is why we are looking for some alternatives, such using fluids on biopolymer basis, for example, glycerol, animal fat, vegetable oils, and different kinds of technology how to minimize or completely avoid the cutting fluids. One of our participants from Turkey has presentation today about minimum quantity lubrication and possibility how to use such technology. Actually, it's well known. It needs a lot of investigations and a lot of costs, high costs with nanoparticles. That is why we are trying to find another way for cooling and lubricating, and we have tried to use cutting with solid lubricants. As you can see here on the slide, it's also not fully studied, and technically and economically in this time we have not enough information, especially for such type of grinding as diamond spark grinding. Next slide, please. On the next slide, you can see, next slide, please. We can see our technical system. It's a conventional grinding process. Maybe we can see a video. I have tried to send a video yesterday. And it's our conventional grinding machine, but with aiding of energy resource. So our wheel body is made from aluminium alloys with diamond grace, And we can see on the top of our video, here is our solid lubricants. Was fed by contact method, and at the core contact we can see a little spark. It makes the process more effective, and we can implement it actually for heat-resistant steels, hard-alloys, super hard materials. This process was invented and researched last century at the Institute for Cutting Tools and Cutting Materials at the Polytechnical University. And now we try to research how to replace or find ecologically friendly cooling technologies such as solid lubricants with different kinds of components to meet the requirements like anti-adhesive, anti-friction effect, less energy costs, less consumptions of diamonds, and we try to compare it with traditional cooling. In this time, we use cooling with irrigation, but the volume you can see on the slide can reach more than 50 liters per minute. That is why our aim of research is replacing liquid cooling, and last years have reported about technology how to make on the metal body some dielectric couple, dielectric coating at the center of our um, diamond wheels. At the next slide, you see our research methodology, and here the whole process, our variable parameters, and you can see how we can connect our hard alloys inserts from titanium carbide. It was a cathode, and our diamond wheel body was anode, high bar with pulse generated connected, and our variable parameters current, different kind of current voltage, pulse frequency, grinding speed, and so on. And measured parameters, cutting force, grinding time, mass of removed material. And we have compared different kinds of solid lubricants with liquid cooling. The traditional we have used striped soda solution in water. At the next slide, you can see our characteristic that we studied and have chosen for our process recognition. It was a specific energy intensivity, consumption of diamonds, productivity, and prime costs. So energy and economically parameters. And as results, next slide, please, you can see three kinds of different solid lubricants, stearine, sebacic acid, equal parts of stearine and sebacic acid, and in comparison with liquid cooling, jet irrigation. And we can see here, for example, productivity, we have with our stearine basic acid share much higher and much lower consumption and costs of grinding. It means that we can use in our future researches these components. And at the next slide, also influence of our specific energy with different cutting speed. It's also can we see that we have a slight change of energy consumption, but a better grinding performance with our stearine and sebacic A. And next slide, please. We can see here the whole results that the most influence of our specific energy intensivity has a cutting speed. We have tried to 65 meter per second, and as the main and most interesting result for us was that this combination of solid lubricants, stearine and sebasic aids, give us more active self-shapering of the diamond and large removal of material, bigger productivity. In this case, we can consider that we can actually replace for small volumes with our next slide conclusions. If we want to manufacture or shaping such kind hard metals as titanium carbide, can replace for small areas our liquid cooling with solid lubricants, and it brings us also practical benefits like tour wear is chip swaps are easier, setup costs very slight, and dry working area is more appropriate for our grinding machines, not only for shaping, also for finishing of hard alloy inserts. For the future, we can say that we will try another components for solid lubricants, and we want to research and see what kind of process lead to temperature rising, chemical reactions, and tribological mechanisms, how it works. Thank you for your attention. I would like to thank you for my colleagues. At the next slide, you will see my colleagues, Alexander Rudnev, Yuri Gutsalenko, Larisa Popani, Elena Svidova, for our collaboration between two universities. And I can answer the questions. Thank you very much for your attention.
Thank you very much, Oksana, and your colleagues for interesting presentation. Maybe our colleagues have questions to Oksana. No questions. Thank you very much, Oksana. We'll be glad to see you next year on this
You are
conference.
a great team. Thank you very much for this possibility to present our scientific results. Have a good days in Lviv.
Thank you.
Thank you.
Dear colleagues, and this will be last presentation in our session, and we are finished our session, and I want to thank you, all our speakers and our organizers, the Vitaly Ivanov and all team from the SUMI and Lviv for organization and for our conference. Thank you very much.
Thank you very much for sharing this session.
Thank you very much.
Замечательно. We are starting the work of the third session of our conference. We will listen to 4 reports with you. I ask those present in the hall to actively participate in the work. We are waiting for substantive questions and lively discussion from you. The first report has a title, development of optimum thin-walled parts, milling parameters, calculation technique. Authors of this report are Sergei Dobrotvorsky, Sergei Kononenko, Evgenia Basova, Lyudmila Dobrovolskaya, all from National Technical University, Kharkiv Polytechnic Institute, and our friend Milan Edl from Czechia, West Bohemia University. Speaker of this report is Sergei Kononenko, online.
Good afternoon, everyone. Research is dedicated to development of optimum thin-walled parts, meaning parameters calculation technique. Thin-walled parts are broadly used in different industries due to its efficiency, lightweight. The next slide, yes. But there are many barriers to surface formation process. The deflection of thin-walled parts is one of the major points. It limits the manufacturing accuracy. Another point is the complexity of errors prediction. Existing solutions mostly consider only the tool's flexibility while the part is supposed to be rigid. So it's necessary to take into account the additional intelligent systems that could be applied in parts production preparation. The developing solution is based on different areas of expertise, such as mechanical, electronics, controls, computer systems engineering, and all these combined represents multifunctional system design. Next slide, please. The aim of the research is to develop the solution that can be integrated into modern manufacture, which meets the needs and visions of progressive Industry 4.0 concept. The intelligent manufacturing solution that will target predictive processes such as CAD/CAM/KI preparation and via endpoints communicate with these systems at the stage of job preparation, where we calculate technical parameters for machining, input expected accuracy, and test all this data to execution of real-time production measurement process. Next slide, please. The research methodology utilizes tabular data collected from mechanical engineering literature, analytical calculations, and finite element analysis to verify the adequacy of certain parameters. The main modulus are thin-walled parts geometry properties and machine specification properties, spindle power, feet, rotations, and tool parameters, number of teeth, diameter of the tool, stick out, length of stick out helix angle, and so on. Also, we input removal properties and cutting properties such as depth of cut, whether we use high-speed milling, and in the results area we get deflection at the end of thin-walled part, maximum stress at the base, and tolerance percentage of initial expected accuracy, and cutting force, rotation per minute, and feet for the performance of the machine. Next slide, please. In the process of thin-walled part manufacturing, undesirable deflections occur in the direction of force impact, and it leads to non-compliance with requirements, the deflection values exceeds the acceptable tolerance zone, and we investigated deflections for most critical points, and for conventional machining, for high-speed milling, and the model of the deflection is formulated including geometry parameters, generalized force, and the measure of material stiffness. Next slide, please. To perform the dynamic high-strain analysis, we used Johnson-Cook plasticity and damage criteria. It's empirical and represented by specific material constants. The analysis allows getting the force components acting in the different directions, including the direction of minimum stiffness of the part. And 9 bursts of the force response can be observed on the graph. Each corresponds to cut in and cut out of the cutter tooth. And additionally, the maximum indicators of the component that reacts in the deflection of minimum stiffness are highlighted. Also, we investigated that during high-speed milling, heating does not cover the entire thickness of the investigated sample. Next slide, please. So in this way, we get closer to architecture of our solution. We used microservice architecture due to its main advantages. It could be consist of multiple running different blocks with its own functions. It's multi-language. It could be multi-languageal and has each component has own database and components independent, with what gives us high execution speed and high fault tolerance in case if one of the components won't work. Next slide, please. General algorithm is presented, and the program starts with the reading of parameters of thin-walled part geometry, the input specification parameters of the machine selected. At the next step, the two parameters, diameter, material, and others, cuts parameters, depth of cut, whether high-speed milling is applied, and we perform the calculation. In case, and every stage we perform validations. Thus, in the deflection component, the verification executes whether the deflection exceeds the acceptable tolerance. The results are stored in the database, so if our tolerance matches technical requirements with our selected parameters, we haven't launched calculation again and just read the previously stored data. Next slide, please. So the program is implemented. Program implemented as a web application. The ability to perform Python scripts for Abacus lets us to communicate with the KI system by launching input file with different parameters and reading the output. The order of common use is selection of machining material, expected tolerance, geometry of thin-walled part, whether it's a flat wall or tapering, the input of the machine specification parameters, selection of the two materials and parameters, removal properties, fit for tooth, unit power, and others, cutting parameters, and calculate in the results area. Also, we have indicators which helps us to observe results, and there are red indicator that means error and machining cannot be performed, or one of the invalids is one of the inputs are invalid, and yellow in case when the parameter is near its maximum, and green one when deflection within the acceptable tolerance zone. Next slide, please. So the conclusion, our solution consists of analytical and applied implementation in the form of the calculation solution. We performed high-speed milling by finite element machining simulation and got parameters of the machining. The solution takes into account the deflection of the thin-walled part, and as further improvements is the extension in terms of dynamic behavior of thin-walled part and consideration of CAM system interaction. The solution represents the basic frame for further development and integration as an additional layer in production preparation. Thank you for your attention.
Thank you very much. Have anybody questions? Maybe you, Sergey Semyonovich? Thank you very much. No questions.
Thank you very much.
Next presentation. Authors of this presentation: Vadim Stupnitsky, Igor Gritsai, Ksyanin, Lviv Polytechnical National University. Name of presentation: Simulation Research of Machining-Induced Surface Layer Operational Characteristics. It was face-to-face. Please.
Good afternoon, colleagues and professors and chairman. No, my name is She Xianning. Now I study at Lviv Polytechnic. Today my topic is simulation research of machining-induced surface layer operational characteristics. Next slide, please. Life cycle of mechanical engineering products depends on a large number of different factors. Most scientific research usually focus on design and operational phase of products. Undoubtedly, the microgeometry shapes of the part, material, quantity of load, surface of the structure parts, conditions of their operation, efficiency of scheduled repair and service are great importance for ensuring reliable and long-term operation of a machine and mechanism. However, a large number of properties of an engineering product are also formed at the manufacturing stage that the designer assigned are met. However, this state is only partially correct. Due to the use of some technology, residual compression stresses will appear in the processed layer of the workpiece, not just as a result of edge jaw cutting, and otherwise, if abrasive processing technology were used, residual tensile stresses appear on the surface layer. The designer doesn't have the ability to influence the formation of these properties, since they are results of a subsequent design stage of the product manufacturing technology. However, the sign of the residual stresses has a significant impact on the ensuring the fatigue resistance of the product. There are many examples of the importance of the impact of technologically processed performance on the optional properties of the machine. Next, please. The last, please. Yes, thank you. Thus, for comprehensive increase in the efficiency of the engineering product life cycle, the creation and implementation of scientific and applied foundations for the design of functional oriented technology is relevant. The function of the goal in the formation of the optional data of technological operations is to provide, by means of concurrent engineering, complex of functional and optional properties of the product, while observing the parameters of accuracy and quantity of surface life, as well as organizational, technological and economic constraints specified by the designer. The results of such problem-oriented modeling are the basis for predicting the impact of technological process parameters on the formation of products, operational properties, an original scheme for determining of residual state on top and the depth of the machined surface is proposed. The analysis of influence of technological operation data on formation of residual stream was carried out by using deformed 3D simulation. Next slide, please. Thank you. The mechanical state of machined surface layer has mainly resulted from the after effects of elastic plastic strains, which occurs in the cutting zone, thermal exposure, and chemical reaction of the machined material with the cutting tool material and with the external technological environment. When the tool is cutting into the material being processed, the wave of the plastic deformation propagating in front of the cutting edge of the tool covers not only the chips, but also the material located along the cut line. Therefore, machined material at the cutting edge itself is subjected to the normal force and the friction force acting in the direction of the shear line. The normal force causes the compressive stress, and the friction force induces tensile stresses of the surface layer adjacent to the front face to the tool. That the surface layer of the part is subject to inhomogeneous plastic strain, monotonically damping along with the cutting depth. Next slide, please. Another reason for the occurrence of residual stresses is the thermal dip process analysis. The outer layer of the workpiece heating up during the cutting process tends to a linear explosion. However, this is prevented by the cold inner layer, which is compressed. When intensive heating, the current stresses on the surface exceeds the yield stress, which causes plastic compression strain of the outer material layer. During subsequent cooling, The outer layer shrinks to the size less than the original by the value, same as additional compression stream. This will be blocked by the stressed workpiece inner layer. Therefore, either the mechanical factor can be dominant and the macro stress of the compression prevails of the on the processed surface or the heat factor. And then a cutting process is accompanied by a significant phase transformation that are significant in density and depth. This phenomenon is sometimes as a strong source of stress formation in surface layer than mechanical and thermal factors. Next slide, please. Hardening of the machined surface layer is in most cases harmful and reduce the performance of machine parts. This is because after plastic deformation of the surface layer mature at room temperature, its specific volume increase and density decrease. One promotes faster diffusion processes at high temperature and the accelerators the processes that reduce the resistance of the material to dynamic destruction. Prolonged exposure to high temperature on the hardened material quickly lead to its intensive softening, which reduces the overall performance of the parts. The micro hardness of the material surface layer is responsible after its operational at high operating temperatures. A sign of burnout of alloying elements may be changed in the parameter of the crystal tricks of the heat-resistant alloys. With increasing degree and depth of hardening of heat-resistant alloy, their fatigue stress when working in an environment with high temperature decrease significantly. Next slide, please. Okay. The methods of determining the depth of residual stress is similar, but the test points for measuring deformations are not located. Along with the less length of processed surface, but into the deep, it's obvious that the modeling of depth pattern should also be done in zone of thermal stabilization of the machined surface. The simulation results are shown here. Next slide, please. The presence local tracks of residual stress during the machining of plastic material. About this plastic material, for example, titanium alloys, is due to the complex nature of the dynamic load on the jaw. Please see left picture. The sinusoidal and dissonant character of the longitude and transverse components of the cutting force cause local hardening zone of the material and local softening zone of the surface layer to appear on the surface. The most representative of this can be seen in results of modeling in deform 3D. Please see right picture. The process of alternating hardness zone significantly reduces the fatigue stress of the surface and the corrosion resistance of machine parts. Therefore, an important step in assigning cutting parameters for such alloys is to reduce the dynamic component of the force action. Next slide, please. Thank you. The analysis of accuracy of modeling was carried out as a result of comparison with the results of experimental studies. Such comparative results were carried out using the methods of measuring the micro hardness of surface layer before and after machining. The analysis of research results showed comparability of the surface hardening value obtained as a result of modeling and as a result of experimental research within 6 to 8%. Next slide, please. The analysis of influence of the technological operations data such as cutting parameters, tools materials, the geometry of cutting wedge, etc., on the residual stress carried out on the basis of rheological simulation in deformed 2D and 3D, allowed us to draw main following conclusions. Now, here are 4 conclusions of this study. Now, the relevant contents have just been stated. So now no detailed explanation will be given. That's all. Next slide.
Thank you very much.
Thank you for your attention.
Thank you. Have anybody questions? No questions. Thank you very much.
Okay, thank you. Thank you, Chairman.
Next presentation. Geometric modeling of lace cutters turning high precision stainless steel tapered threads. Authors Олег Аниська, Юлия Медведь, Виталий Панчук, Vesna Rodich, and Christian Bartz. Ivano-Frankivsk, National University of Oil and Gas, Independent University of Banja Luka, Bosnia and Herzegovina, and Technical University of Cluj-Napoca, Romania. Speaker Олег Аниська, please.
Thank you. Please, the next slide. And our team prepared for you, special for you, this research. And bigger please for all, yeah. The main problem of our modern drill string. Yes, it's our team prepared this because we are from University of Oil and Gas. It's from one hand, and we are from Cathedral Department of Machine Building, and machining of drill ring is our specialty. So taper thread 2 joints used for all oil and gas drilling string, and maybe pipe casing string. It very often deal with aggressive carbon dioxide gas environment, and it imposes high requirements on the high precision construction, anti-vibration, and of course protection in anti-corrosion protection and properties for this. We have to consider in tightness and other properties for this consideration, but it's bigger, please. Of course, thank you. It's specialty from oil and gas drilling string, but about specialty of our department, machining of this string, the most important problem for us is to ensure efficient turning of high precision. You can see this. High precision threads from hard machined high alloy steel with significant anti-corrosion properties, properties, anti-corrosion properties, because gas carbon dioxide. This problem is solved by using the appropriate materials of cutting part of the last tool from one hand, and from geometric of inserts. However, manufacturers of world that design these inserts for taper thread do not resort to the variability of their geometric parameters. Has crucial for the cutting process. It's very interesting for us because it's our this report is deal with our scientific researchers. Next, please. It was main problem, but what about the geometry of a regular thread tool? Scheme, you can see scheme of the thread machining with a zero rake angle last tool. Zero rake angle last tool is special produced by a world manufacturer of this instrument, machine tool instrument and tool instrument. And this approach is practiced by the vast majority of tool manufacturers, apparently because they do not have a method of calculating the cutting tool edge profile. So calculating and method of this calculating is our problem, and we solve it. Therefore, is our aim and problem of our work. Sorry, it's not good for everything, sorry. Okay, thank you. So, the profile of which this insert of carbon insert of our material is a function of back rake angle, and basing on this, the model is to create a software interface that can be used to make high precision taper threads from different materials, including stainless steel. Thank you. So the last, next, please. Can I? Okay. Here, our research methodology by scheme, last threading cutter with the non-zero value of the back rake angle here on the left, and the formulas. So equations from this picture and scheme are presented on the front, on the right. Thank you. Next, please. Okay, thank you. Okay, here the own subject you want to explain you, because the standard of threading is standard about archimedical screw surfaces, but we know that the last tool technology is provided only non-archimedical screw surface, but convolute screw surface, and the profile of this thread is profile supposed by this formula Zx. It's formula, not algebraic. So, thank you. It's the next, please. And due to this new methodology of my colleague and me, we propose the methodology to predict thread profile manufactured by LAS, and we received these equations and two equations of calculate the alpha long and alpha short. It's half profile angle from left and from right, as you can see on these slides. Next, please. Next, please. And from this theory and from that before, the picture before, we received by using our application this table and this scheme of thread profile. Thread profile, the red is standard, thread profile blue is received by our, and green so the curve that show that we want to show you about mistakes. Send the next, please. It was result, and according to that result, we receive this table, these two table that show our result in the number. And the next, please. And conclusion. And the main conclusion is based on the visualization. It is confirmed that the actual profile of the sites of the tool joint thread made by cutter with a non-zero back right angle is actually curved. And next more, obtain geometrical model gives possibility to predict the precision of thread made from different steel sorts, including stainless steel, especially for carbon dioxide prediction in the drilling. So, the next, please. Thank you. Thank you very much for your attention. And
thank you very much.
Okay.
Have anybody questions? No questions.
Thank you very much.
Thank you
my
very
colleague.
much.
Chair.
Next presentation. Optimal milling conditions for complex shape symbol components. Authors Anton Germashev, Yuri Vnukov, Mark Kuchegurov, Viktor Lagaminov и Bert Lowers. National University Запорізька Політехніка and one Belgium participant. I would like to draw your attention to the fact that Professor Vnukov is with us again after the break. I hope that we will meet more than once and face-to-face, maybe this year in September in Odessa, maybe. Speaker Anton Germashev, online.
Hello. Thank you very much. So let's start. The next slide, please. Milling of symbolic components is really challenging task, which is limited by the so-called regenerative effect and vibration, which significantly limited productivity of this process. Next slide, please. Milling of symbolic components become possible with when appear the machine tools with the high-speed spindles, and this process has certain specifics, which is low radial and axial immersion. So, with the conventional machines, we receive the productivity with the increase in the material removal and immersion of the tool. For now, with the high-speed machining, we increase in the spindle speed and feed. The next slide, please. Also, with the high-speed milling, the temperature is not a limitation factor anymore, because the tool in contact with the workpiece just little amount of the time of the revolution, and the other time we have a good cooling of the tool, so that's why we can increase spindle speed significantly. Next slide, please. This is actually the specific of such process. So we have the low radial and axial immersion. So this process is highly interrupted. So we have the cutting moments, and then we have the free movement of the part and tool during the next cutting process. So this is the main specific of the process, and it should be taken into account when we are discussing the mechanics of this process. The next slide, please. It's widely known that for solving the task of the stability in the milling is used the so-called regenerative theory proposed by Tlusti. However, for now, for the high-speed machining, this system is not closed anymore because we have cutting force, and then we have some free movement of the part in detail. So we have free oscillation of the part and tool. That's why proposed classical approach is not relevant anymore. The next slide, please. We did some investigation and measured the chatter frequency during the cutting test. We did it artificially. We significantly reduced the spindle speed to reach the conditions where the cutting time higher than the period of the chatter of the self-excited oscillation, and we reached the conclusion that the chatter frequency changes significantly during with the changing of the spindle speed, and even with the feed direction. So it's different chatter frequency for up and down milling. And also this frequency significantly different from the initial frequency, which is also not suits the classical regenerative theory. The next slide, please. So basically, our results show that the main influence on the surface formation and the behavior of the milling process is position of the tool and the position of the part when we are discussing the milling of thin wall components and high-speed machining. So very important, the position of the part, if you're talking about thin wall details, thin wall parts, position of the part at each consecutive cutting process. The next slide, please. So we're able to observe here, so depending on the position of the part at the moment of the tooth entrance, of the each moment of the consecutive tooth entrance, this process determines the quality of the surface finish. The next slide, please. It's not the chatter anymore put significant influence of this process. It's mostly the position of the part and position of the tool, and all this in the dynamic process determine the quality if we are talking about the high-speed machine. The next slide, please. So just a couple of words about the regenerative theory. So it's widely used to determine the stability of the cutting process, and the most successful works is dedicated to the Budek and Altitas and other scientifics. So to determine the stability, we are building the stability lobes, and with this approach, it's possible to increase the efficiency, to increase the axial depth of cut during the cutting process. However, it's important to notice that at the thin wall machining, when we're talking about the blades, impellers, it's not relevant to increase the axial depth of cut because it's limited by the parameters of the detail. The detail is complex shape, so it's not necessary to increase the axial depth of cut. It's usually really low to determine the good quality of the complex shape surface. The next slide, please. And even the regenerative theory, which is widely used for determination of the stability, says that if we start to deal with the interrupted machining, with a highly interrupted machining, the stability significantly increases. The next slide, please. Here's the experimental setup. So our workbench. So we use the displacement sensor, and the most rigid part in our workbench is thin-walled part. And we determine the behavior of thin-walled part during the cutting process. Also, we have the special system which is measure contact between part and detail, between part and tool, sorry. And we are able to determine at what moment the cutting process occurs, and at what behavior, what displacement, what movement the part doing during the cutting process. The next, please. Here is a photo of our experimental setup. The next slide. This is our approach. So it's based. So we are determining the position of the part during each start of each entrance, each cutting process of the consecutive mill of the consecutive tooth of the mill. So the more difference between position of the part, the lower quality of the surface finish. The next slide, please. Yeah, here shown the real example. So we were able to observe the red triangle is a moment when cutting process starts, and the black sign is the moment when cutting process finished. So we are able to observe that if we have big differences between position of the part, it's significantly reduced surface finish. The next slide, please. Here is shown just some experimental results and surface quality. So we are able to observe here that if we have big difference, big peak-to-peak value of the point of tooth entrance, the quality is significantly reduced. So this is a real experimental test. And the next slide, please. This is also shown just some examples where we reached the good cutting conditions and where we have the big value. The next slide, please. Also, we made a correlation analysis to prove our approach. So we're able to observe that chosen by us parameters show an influence on the surface finish. The next slide, please. The next slide, please. We propose the analytical prediction. We propose analytical prediction and build the model with a single degree of freedom with the influence of the system with the triangular impulses. The next slide. So here I show our analytical approach. The next slide, please, and the cutting force. And the next slide. And here is the results of our analytical approach. So basically, it's a polar resonance, which is well known, and that it's also a well-known fact that the spectrum of the milling process, of the high-speed milling process of the thin-walled components is consisted from the infinite number of high harmonics. That's why the resolving of our analytical approach shows that we have some peaks where the quality and of the machining reduces significantly. And the next slide, please. So here is the experimental validation. So it's shown that our experimental results is validate our theory, and we put parameters of our experimental setup, build the chart of the polar resonance, and we're able to observe that when we have the big values, the quality of the surface finish is reduced. On this slide, I will cut myself down because we are limited in time, and I think this is the main slide which is shown which is proof our analytical approach and the approach of our investigation. Thanks for attention. I would really welcome to hear your questions. Yeah, if you have time, I can continue. Yeah, but it's a lot of experimental results will shown then. But I think this is the main, and I see in the time that we are done.
Finish?
Yeah.
Okay. Thank you very much.
Okay, thanks.
Have you questions? No questions. Thank you very much, Anton.
Thanks.
We finish our session number 3.
Thank you very much to Professor Antononi for his contribution to his hard work and this Now is a coffee break till we can
Мене не видно? Добре. Так, добре. Так. Але я не зовсім зрозуміла, як зробити фон. Так ви хочете? Так. Ну, я бачу себе, бачу організаторів, бачу гарний. Так.
Okay, let's start. Good afternoon, dear colleagues, everyone. I will be led the last section today. It's called Material Engineering. First of all, let me introduce myself and other participants in this section. My name is Mykola Melnichuk. I am head of Department Material Science at Lutsk National Technical University. Our section includes the six research. Some of them is prepared from collaboration in the other university, and more of them was presented by online. I would like to notice that you should following the conference rules, because we have limited time, and we must each participant, each speaker have until 8 minutes for present your research, and 2 minutes for question and answer for discussion. I invite the first presentation, the topic, the ion bombardment modeling as a component of the structure engineering of nano-periodic composite structure. Natalia Pinchuk, you are ready?
Yes, I am ready.
Okay, let's start.
Good afternoon, dear participants, dear colleagues. Thank you for possibility to show you my research work. First of all, I would like to say that one of the most popular directions of the nanotechnology is associated with the creation of high solid nanocomposite coatings. the study of fast structural states of the materials and its physico-mechanical properties. Based on structural engineering, such studies open up a new possibility for the prediction formation of the structural and properties of coatings during the deposition process. The structure of the obtained coatings can be influenced using various technological conditions of vacuum arc deposition. Turn back, please. Slide. The purpose of this work was simulate and study the effect of particle energy on the formation of nanoperiodic composite structure in the process of vacuum arc deposition. Next slide. Computer simulation of ion plasma implantation was performed using the TRIM program in mode monolayer collision steps. Coatings were obtained on the modernized installation Bulat 6M, which additionally equipped with a generator of high voltage pulses implied to the substrate during the deposition process. The pressure of working atmosphere during the deposition of nitride layers was about 0.6 Pascal. Structural investigation of the samples were carried out with using the installation drone 3M, and in all investigation was used cuprum alpha radiation. Next slide. First of all, we decided to discover we show you the result of calculating the distribution of vacancies of irradiated ions, which with energy of 230 volts and 1000 volts for different iterations. The depth of the layer subject to radiation damage with the formation of vacancies was about 3 nanometers for particles with energy 230 volts and about 4 nanometers for particles with energy of 1000 volts. It can be described on the basis of the mechanism of formation of the thermal peak. This mechanism is based on the fact that with an increase in energy of implanted ions, the volume occupied by the thermal peak generated by each collision increases. On the next slide, we can see distribution of ions during bombardment of the MON coatings by titanium ions. We can conclude that with increasing of this potential and iterations, the depth of the layer subjected to radiation damage increased too. The next slide. The next stage of the study was to investigate the structural and fast state of multi-layer TN-MON coatings. The result of X-ray diffraction studies are shown on this slide. We can see the formation of polycrystalline state with separated layers of TN and MON. The next slide. After determining of substructural characteristic, it was established that in these coatings obtained without addition of pulse potential, the crystalline size was about 14 nanometers for the TN layers and 7 nanometers in the MON layers. Microdeformation was about 0.8% in coatings obtained without impulse potential and 0.47% with high voltage influence. Such a decrease in microdeformation can be associated with the relaxation process under high voltage, high energy impact, at which displacement cascades after formant. The hardness of these coatings was about 47 gigapascal. The next slide. Okay, is this okay? No, turn back. Thank you. Similarly with the previous type of coatings, we decided to calculate the distribution of vacancies at radiated ions during the deposition of multi-element coatings, high entropy. From the data given on the tables, it can be seen that the heavier ion penetrates deeper into coatings and creates more defects. Though the thickness of the radiated effects layers about 5 nanometers, we can change the fast structural state in the format layers. On the next slide, we can see diffraction spectra for the multi-element coatings. We can see that in this case, we receive the formation of three-phase state. Is formed from two phase from FCC and one phase BCC crystal lattice. In this case, the gamma mod 2N Mo 2N phase forms in the molybdenum nitride layers. The hardness of these coatings is about 54 gigapascal, which is higher than the for similar condition in the multi-layer coatings TMON system. The next slide. Summing up, it is shown that the four nanoperiodic composite coatings with the monometallic state of nitride layers, the use of high energy impact in a pulse form allows the formation of more equilibrium structure with different types of crystal lattice, such as MoN. The next slide. Of the substructural level, the use of high voltage impact of ions can reduce the macro deformation of crystals and increase their average size. It was revealed that in nitride based on multi-element high entropy alloys, it is possible to achieve an increase in hardness up to 54 gigapascal. And I would like to say that since the trend of modern material science is associated with decrease in the thickness of layers of several nanometers, the limitation of this study do not take into account the influence of the interface between nanolayers. That is why further research is planned will be connected with this investigation. Thank you for your attention. Do you have any questions?
Thank you, Natalia, for your report. Dear colleague, dear colleague, despite the fact that we are working hard all day, I hope you will be more activity in the discussion because it's very important, I think. The main advantage of your method, if we compare with the other well-known methods.
Okay, the main advantage in our method it is use of impulse potential, especially together with constant potential. Because the collaboration of these different types of this potential leads to increase of mechanical and chemical properties of our coatings obtained by vacuum arc deposition.
Thank you. Any questions? Okay, thank you for your very interesting report and research.
Thank you.
I would like to invite the next speaker, Anton Tsaritsky. is research topic optimal design of composite shell sandwich structure with a honeycomb filler.
Yes, good afternoon. Do you hear me?
Yes, we hear you.
Yes, good afternoon to all participants and organizers. So, the presentation. Currently, I cannot see the presentation. This is it. Yes, please, the next slide. Thank you. So, one of the important ways of increasing the efficiency of bearing structures is using the sandwich structures, which consist of two thin composite face sheets or skins and lightweight honeycomb filler between them. To design a sandwich structure of minimal weight, we have to select a design model that is adequate to the geometry of the structure and the range of external loads. Considering the features of composite sandwich structure, we made an attempt to suggest another approach to searching the optimal parameters of such structures. Next slide, please. And that was the aim of this work, the development of a technique of parameter optimization of composite sandwich shell structures with the improved mass efficiency. To achieve the aim, we formulated two tasks: the analysis of effectiveness of the sandwich shell structures and preliminary optimization of its properties, and weight optimization of the multi-section composite sandwich shell structure of the launch vehicle payload fairing that we selected. Next slide. And this is the object of our research, payload fairing of the launch vehicle. On this slide, you can see its shape and sizes, as well as the initial data for the optimal design procedure, such as dimension constraints, operating conditions, main load cases that you can see below on this slide, and materials supplied and their physical and mechanical properties. Next slide. On slide number 5, you can see an example of payload fairing loading at a specific moment of time. Distribution of bending moments, shear forces, axial forces, and excessive pressure. Next slide. For the optimization in the finite element analysis software, the payload fairing is presented as a system of shells supported by stiffening rings. Conical and cylindrical sections are represented by the composite shell finite elements that include 4 layered bearing skins and a separate layer for the honeycomb core modeled homogeneous in volume. For the spherical tip, a single layer shell finite element has been used. Stiffening rings and elements of joint were modeled using beam elements. For the correct representation of the joint between the payload fairing and the adjacent sections of the launch vehicle, all these sections were added to the model. Next slide, please. Before the optimization, it was reasonable to analyze the basic design of the payload fairing, and in this slide you can see the results. The Mises-Hill criterion for the layers of bearing skins, shear stresses in the honeycomb core, buckling load factors, mass of both the bearing skins and the honeycomb core, and the total mass of sandwich structures. Please, next slide. Slide 8 shows the approach to the weight optimization of the composite sandwich payload fairing under thermal and mechanical loading. The procedure is divided into 4 blocks. The first block incorporates the preliminary analysis of flight conditions to get necessary boundary conditions in form of heat fluxes and temperatures. Also, here we provide the analysis of the thermal protection plotting. The second block allows selecting the optimal thermal protection thickness, height and cell size of the honeycomb filler, and thicknesses of bearing skins. Additionally, this block helps to estimate permissible ranges of temperatures of the inner and outer surfaces of sandwich shells and bearing capacity of the rational variant in all critical areas, taking into account the deteriorations in the physical and mechanical properties of materials due to heating. The third block serves for further reduction of the payload fairing weight, optimizing the structure of the filler by varying the angle of opening of the cell of a regular hexagonal shape and shape coefficient in each section of the fail. And finally, in the fourth block, different technological imperfections are taken into account and analyzed. And finally, check calculations are performed to reveal if the structure is strong and rigid enough. Please, next slide. And again, next slide. As a result of the proposed multi-stage optimization technique, there was found a way to select the optimal relations between thickness of the thermal protection coating, height and cell size of the honeycomb core, and thickness of bearing skins. Next slide, please. This slide presents the same table, but for the payload fairing design obtained after 2 blocks of optimization approach. As you can see, the mass has become 16% lower compared to the basic variant. The third block makes the structure lighter by 5.63% and 21% in total. And the last slide, please. The research carried out allowed solving the multi-parameter problem of the optimal design of composite sandwich structures with a honeycomb core. To achieve this, the optimization process was divided into several stages. Implementation of the proposed approach for a real object has revealed its effectiveness in form of significant mass reduction compared to the basic design. The results obtained allow further development and improvement of the approach by including some auxiliary structural elements in composite sandwich structures with honeycomb filler. Thanks for your attention. That's over.
Thank you, Anton, for your presentation. Very interesting research. Do you have a question? Colleagues, maybe someone online? No? I have. Anton, mine piece of your research was implementing in real industrial. Maybe you have interesting from industrial in your research.
Well, this research was carried out for a real payload fairing, so I can say yes, it was done for a real-world object.
Okay, clear. Thank you. Okay, the next topic was prepared in collaboration to other university, Luz National Technical University and National University of Life and Environmental Scientific of Ukraine. And present this topic will be Olga Zaleta. The influence of synthesis modes of operational properties of oxide ceramic coatings on aluminum alloys. Olga, are you ready?
Good afternoon to all participants and organizing committee. I'm glad to see you here today. My name is Olga Zaleta, and I would like to thank you very much for the opportunity to take part in this esteemed scientific event. Well, I guess I need help with the presentation. Could you help to show it on the screen? Please help me if you can. Can you hear me? Can you answer my question? Oh, it's great. I can see. Yes, I can see. Thank you very much. So it was the theme of our scientific investigation was presented. So I guess I can start. The topic of our work is the influence of the synthesis regimes on the working properties of oxide ceramic coatings on the aluminium alloy. Thank you for poster 2. Let it be. The problem of the ensuring the reliability of elements of technological equipment construction which are operated under conditions of the friction was and well, still is in the center of attention on engineering practice. Certainly, this problem is of growing importance and it gets new accents in connection with modern trends of technological development processes which are characterized by more rigid operating modes of the equipment. So today aluminum alloys are widely used in aviation, automobile constructions and building constructions due to their good operational properties. The feature of dualumin is combination of low density, high ductility and specific strength. The advantages gives us more possibilities with operating in the equipment. However, the rapid development of modern technologies requires improved operational properties of such alloys. To solve this problem, work surfaces of the parts are covered with a protective coating with predictable properties. Besides, according to the widely used chemical and thermal analysis of the coatings, we must pay attention on possible environmental problems and other negative effects that are associated with intensive heating of the parts that leads to changes in its metric structure and scale formation, surface curvature, etc. At last time, the competitive existing method of the surface hardening is a method of coating creations on the weld metals by plasma electrolytic oxidation as a new technology on intensive anode treatment of metal surface. Please swipe poster 3. Thank you. The purpose of this work was to investigate the influence of the mutual electrodes arrangement on the properties of oxide ceramic coatings, which are synthesized on alkaline electrolyte and in the plasma of spark discharges on the 2024 alloy. To achieve this goal, electrophysical parameters of the synthesis process of micro-hardness and wear resistance of oxide ceramic coatings, which are synthesized at a different distance from the electrode, were investigated in our work. This shows the poster form. I'm sorry, I can't see the presentation. I saw it, but I can't see it now. I don't know what is the problem.
You can see your presentation?
No, I couldn't see on my screen, but I can't see it anymore, and it's hard to understand if I say everything right. Maybe you will turn off it and then show it the next.
This one?
Maybe participants could see that, but I can't see. It's hard for me. Oh, yes, I can see. I will answer you now. One moment. Poster form. Yeah, research methodology. Thank you. That would be. So as you can see, for stitching we used a plastic bus with a length of 5 meters and the radius of 0.1 meters for the synthesis of the coating by the plasma electrolytic oxidation method. The auxiliary electrode, made of stainless steel, was placed at one of these ends. The working electrode, made of aluminium alloy 2024, was placed at the distance of 0.05 meter to 4.5 meters from the auxiliary electrode. Electrical pulses of anode and the cathode voltages were applied to these electrodes. Also, you may see from the poster what exactly equipment we used for measuring process parameters. There were wattmeters, the microscope, micro hardness tester, and friction machine. Show the poster 5, please. Next, the next slide. Yeah, it is. Thank you. So, poster 5 presents a schematic diagram of the devices and voltage diagram. Here, at the working electrode 1, in the electrolyte 2, in the spark discharges form, plasma chemical reactions were developed. As a result, the metal surface was oxidized and ceramic coating was synthesized. Let's swipe poster 6. Next, please. Yes, it's right, poster. This slide presents a schematic diagram of measuring electrical parameters in the electrolyte beds. Here we have the source of anode tension, the source of cathode tension, volt ampermeter, voltmeters, the base, auxiliary electrode, and the measuring electrode and the working electrode. The next slide, please. Thank you. Poster 7 gives us detailed information about the experiment, such as the composition of the electrolyte, current density, and synthesis time. As you can see, the experiment was repeated 3 times. It means that 3 test samples were used. This table indicates that current density has a constant value. It means that the density of anode current was 10 amperes per decimeter, and the density of cathode current was 7.5 amperes per decimeter. These values gave us the specified coefficient 0.75. Let's see on poster 8, if you don't mind. Thank you. In the synthesis of oxide ceramic coatings, the stage of formation of spark discharges on the surface of the sample is very important. Plasma is formed within 3 to 5 minutes. The voltage in this area increases. You may see it on drawing B. As the coating thickness increases, the voltage at the anode gradually decreases. The increase in the anode potential outside the Faraday section leads to the breakdown of the dielectric of semiconductor film on the anode, which is formed during the passage of the Faraday section. The breakdown occurs due to the transition of electrons from the valence band to the conduction band. The temperature in this channel rises sharply. The electrolyte dissociates and ionizes, and the plasma slot is formed, in which the plasma chemical reactions of the oxide synthesis are released. You can see it on drawing C. In places of discharge, the solubility of the oxide decreases, and at the same time increases the release of gas. Below are photographs of aluminium alloy samples before and after plasma electrolytic oxidation treatment. Let's see poster 9. Can you swipe it? Yes, thank you. So, as you can see from poster 9, the plasma electrolytic oxidation process takes place in the anode and cathode modes. The corresponding voltages, measured by voltmeters, are stabilized in a few minutes. The initial rapid increase in such voltages is due to the breakdown of the conductive film on the metal. Depending on the composition of the electrolyte and the distance between the electrodes in the synthesis of coatings, the voltage values of the anode, VA, and the cathode, VC, were verified. After the breakdown phase of the oxide film, the synthesis process proceeds evenly, as evidenced by the slight change in voltage at the anode over time, which is characteristic of the electrolytes. Poster 10, please. I'm sorry, something is wrong. I can't see the presentation. One more time. Can you see it on your screen? Maybe I will continue without the picture on my screen. It should be the diagram on poster. Yes, yeah, it's exactly. I mean. So, the stability of the process over time allows to measure the total voltage at the length of the cell for different distance between the electrodes. We can change the slide to poster 11. Thank you. Studies of the thickness and micro-hardness of oxide ceramic coatings, which are synthesized in different electrolytes and the different distance between the electrodes, are presented on this slide. You can see that. It has been experimentally established that the coatings synthesized in the electrolyte S2 at the distance greater than the critical from 0.5 to 4.5 meters are thicker than in the more doses electrolyte S3. The macro-hardness of oxide ceramic coatings ranges from 600 kilograms on square millimeters to 1,100 kilograms. And now we may change the poster to poster 12. This slide shows the photos of samples after wear resistance tests. As a result of the test, we have gotten wear traces with the help of test samples, which are described in this figure. Secondary structures on the surface of the opposite elements are formed as a result of complex physical and chemical processes, such as temperature increase, temperature and chemical changes in temperature and chemical reactions. Let's change the slide. Well, if you be able to see the poster 13, you can see that coatings synthesized by plasma electrolytic oxidation have low porosity. This is due to the fact that the coating is synthesized at high temperatures, which causes the pores to melt. The figure shows fractograms of the synthesized zirconium alone. Let's change the slide. Thank you. The synthesized coating contains in some areas inclusions in the form of the branches. Obviously, there's the Cooper inclusions. And the poster, 15th place. It's something wrong with the presentation. It is the last slide we have to see because the important information is on it.
It's following the timeline in the conference.
Okay, I will try to finish. It will be a last slide with the important information. I'll say a few words about it. If you can see the slide 15, I'll just explain what was showed on the slide. Well, maybe I'll just say some words and will not use the time. So we have found that the distance between the electrodes also affects the wear intensity of the oxide ceramic coating. During the experiment, the intensity of deterioration of the oxide ceramic coating and which stage was determined. So the first stage of the synthesis where intensity in the largest for oxide ceramics, which is synthesis at the distance of 0.5 meters. So therefore, the secondary structure of the opposite elements may soon be developed here. And this part is a characteristic of the three samples studies. The stability of the formed secondary structures, which are estimated, were ambiguous. So we can say about two curves that angle of the inclination of which practically does not change during the next 1,000 meters. Well, I guess I will say some words about conclusions will be finished. So the results of our work showed us that the voltage between electrodes varies almost literally regardless of the electrolyte composition and the distance between the electrodes at the constant current density. And it is important that the value of the synthesis voltage is influenced by the composition, electrolyte concentration, and the distance between the electrodes. Then we received results that show us how concentration we need for the best results, what voltages we have to create to have the best results, and we find out other values of factors that have an influence on the experiment processes. And now I guess I will be finished. Thank you very much for your attention, and I will be glad to answer your questions if you have.
Thank you for your speech. Colleagues, do you have a question? No. One from me. Olga, do you have a plan for further research on this topic?
Well, we have many scientific plans that may be realized in a measure of this theme. So we plan to conduct X-ray structural analysis by establishing the phase composition of the obtained contents. It means that without the distance between the anode and the cathode affect the fast composition of the coating. And it is also important to establish the effect of distance on the porosity of such coatings.
Thank you for your answer. Thank you for
You're
your
welcome.
speech.
Thank you very much too.
Let me introduce the next topic, research, that was prepared in international collaboration between Sumy State University and Technical University in Košice. This speaker, Ruslan Zaloga, the topic research rational choice of a material or for orthopedic insoles based on the mechanical characteristic of practical applied purposes. Ruslan, you can start.
Can you hear me? Do you hear me?
Yes, yes, we hear you.
Hello, everyone. I would like to present our research. Next slide, please. Customized orthopedic products are attracting an increasing interest from the research community. In order to reduce complaints about the musculoskeletal system, it is important to choose the right footwear. Orthopedic insoles have a corrective effect on the wearer. They are designed to reduce and adequately distribute plantar pressure between the points of support and thereby minimize the stress to which these points may be subjected. Physical and mechanical properties such as elasticity, compressive stiffness, and the coefficient of friction are generally considered key requirements for evaluating and selecting suitable materials for orthopedic insoles. The current choice of polymeric materials for orthopedic insoles and footwear is based on empirical evidence. In many cases, this choice is made subjectively because there is no information regarding the mechanical properties of each material and their in vitro interaction. Next slide. Considering the wide range of orthopedic materials and limited selection of suitable characterization technologies, and the fact that the effectiveness of orthopedic insoles continues to be highly dependent on the repeated trial and error experience of individual orthopedists and practitioners, the aim of the study was to develop objective quantitative evaluation criteria for orthopedic insoles material selection based on their mechanical characteristics and the purposes of their practical usage. Next slide. For this research, polystyrene, polyethylene, polyurethane, polypropylene, and ethylene vinyl acetate were selected for comparative analysis. They are all foams. The last three of them are used the most commonly. Next slide, please. We examined the abrasion resistance of the materials. In polymers, two very different wear mechanisms can occur, namely cohesive and interfacial wear processes, as schematically shown on this figure. The diagram illustrates the force acting on the sample in a tensile manner. In this case, internal stresses arise. Next slide. The first formula can be used to calculate these stresses. F is the force acting over the cross-sectional area A. The formation is calculated with the second formula, where delta is the change in the sample length and L0 is the initial sample length. Depending on the material and the magnitude of the load on the sample, it will exhibit elastic or inelastic properties. Based on the results of testing materials with different stresses, it is possible to determine the proportionality of strain or elastic modulus using the third formula. Shear stresses occur when translational forces are created parallel to the surface area of the material. A sample comparison for the mentioned materials was performed using an ASTM G133 friction tester. All samples were weighed before and after testing using a 4-digit decimal scale. The difference in weight before and after the test and the coefficient of friction were evaluated. This difference was analyzed to see how much material was removed from the sample. The percentage of wear loss was calculated for each specific sample in both 1 hour and 2 hours of testing. The determination of rebound elasticity was carried out according to the method described in ISO 8307/2018. Flexible cellular polymeric materials determination of resilience by ball rebound. Next slide. The research showed that when choosing the material for the insole, several factors must be taken into account. The material should be technologically easy to manufacture, have good durability and availability, favorable mechanical properties, subjective comfort, and be affordable. Next slide, please. The results also show that cavities in the insole will generate cushioning if the selected materials are not too stiff. Increase in material density and thickness will further enhance stability. Another important aspect when choosing a material is the ability to withstand permanent deformation. There are two types of structures, open cells and closed cells. The open cell structure absorbs energy due to the deflection of the struts when the air is pushed out, compared to a closed cell where the walls flex when the air is compressed. But both procedures will deform under a certain load, but will return to their original shape when no load is applied unless the load becomes too high and causes ductility. Next slide. Because its properties are on average superior to those of other materials, polypropylene was chosen as the most suitable material for the production of insoles. A more detailed list of its properties is presented on the following table. Polypropylene material has high elongation at break, high tensile strength, and high abrasion resistance. In addition, the innovative foam remains very flexible and soft over a wide temperature range. It also has good chemical resistance. Next slide. The main findings from the study are that field density is the dominant factor in material and energy consumption, while layer height has the greatest impact on production time. Also, it simplifies the process of choosing the most suitable orthopedic products. As a result of the research, a block diagram was developed that will help in the design process of orthopedic insoles. The entire success of orthopedics depends on the patient's weight, shoe style, and lifestyle. Patient weight is critical information that the laboratory must have in order to make the right choice of material. The style of shoes a person wears will influence the type of orthopedics that suits them best. Knowing the type of orthopedic products, now we can choose the base material for the manufacturing. Multiple materials were compared and polypropylene was found to have the most suitable properties. Mechanical tests have confirmed that optimal stiffness rises when with increase in compressive load. This study, for the first time, provides quantitative evidence for the importance of optimizing the stiffness of cushioning materials, at least the foundation for techniques that allow the optimization of material selection in the clinics. It also clarifies and complements the previous studies done by other research. Next slide, please. Thank you for your attention, and now I'll be happy to answer your questions.
Thank you for your report. One question from me. In your study, you had analyzed only synthetic plastic, but any renewable material which you use for additive manufacturing. Why you did it? Why you didn't it? Why you don't study any renewable material like polylactide, PLA, or oxyazide?
We had some time constraints. Currently, we review some possible variants of development of this research, and we will definitely look into these materials because we are interested in current trends with renewable materials and care for ecology and such.
Thank you for your answer. Colleagues, do you have a question? No? Thank you. The next topic was also prepared by international cooperation between Luz National Technical University and Airport Lublin. The topic: structure and properties of surface bandage shelves for the gas turbine engine blades. This topic was report Natalia Zaychuk. Natalia, you can start. Natalia, we can't hear you. Can't hear you.
Sorry. Good afternoon to all present. Glad to greet everyone. Thank you for the opportunity to report our work. A group of authors and I studied the structural change and change in the properties of the bandage shelves of the aircraft engine blades after soldering. The basis of a modern aircraft construction is a gas turbine engine. GTA blades are the most numerous parts. Their total number in the engine is about 3,000 pieces. The reliability of gas turbine engines depends on the compressor and turbine blades reliability, as they are the most loaded parts. They are located in the gas stream and in the area of high temperatures and air are designed to change the parameters of the engine and consist of a root of shank, which serves to attach the blade in the housing, the working part, the blade washer, and the top in the form of a spike on which the bandage tape connecting shells is put on. The next slide describes the reason for the destruction of the bandage shells in the operation of the working and nozzle blades resulting from significant contact stresses under conditions of friction and vibration and the contact points on the shelves. There is increased wear of the contact surface compared with the pen and the blade look. Ensuring parameter identification for rising operation temperatures and aircraft engines service life sharply intensify the processing that lead to damage and destruction of the blades contact surface, limiting their service life and reliability. In general, the following defects may occur during the operation of the blades, such cracks in the main metal and surface cracking due to fatigue wear, damage the surface layer of parts due to corrosion, increasing operation of contact surface under the conditions of friction and vibration. From the experience of aircraft repair units, it is known that one of the most profitable and effective ways to repair many engine parts is building. However, the result of studies of the mechanism of wear of contact surface allow conclusion that the best option to strengthen the blades is to create in the wear zone a layer of highly heat resistant and wear resistant material different from the blades material. Method for studying the structure and determining the chemical composite are presented on the next slide. Surfacing on structure and properties of surface banded shelves for the gas turbine, the blades of the wear resistant and heat resistant layer of VTN1 alloy performed by the vacuum arc method. The studies were performed according to standard methods. Next slide, please. The object of research was the shelf of the aircraft engine blade. We can see to figure 2. The samples were cut from different parts of the compressor blades bandage shelves. The study subject was samples cut from bandage shelves on which the light was quantitative applied and one form from the shelf which contained a defect in the form of a drop. Also was examined. On the next slide, we can see image of the section of titanium alloy VT31 and the image of the samples surface with soldering, with quality soldering and defective area. In particular, in this work, we studied the surface of samples made of titanium alloy VT31 cut from different parts of the compressor blade. The surface structure indicates that the material is viscous and ductile, difficult to cut and prone to sticking. Next slide, please. Spectral analysis performed on soldering shows a homogeneous distribution of chemical elements on the sample's surface. The defective coating surface is characterized by a straightly lower roughness than high quality soldering, and there are sometimes small cracks which don't pass the thickness of the coating. Local analysis of the pots shows that they differ in element. On the next slide, we can see comparison of the composition of the content of chemical elements in different parts of the studied simplex figure 6. Comparing the average values of the quantity composition of quantitative soldering, defective area and base material is shown in table 1 on the next slide. The next slide, please. Next slide contains a table 2 with a date on the change in micro hardness of the test samples. We obtained data from 4 sections of shelves. The first, it's the surface of the sample from the alloy VT3-1. The second part is the surface in the sample with detective relied soldering. Third part, the surface of the sample with high quality relied soldering, and fourth part is the pure relied grains. Next slide, please. The figure 7 shows the histograms of comparison of the obtained average values of the micro hardness of the samples. A characteristic feature of titanium alloys in the low modulus of elasticity, which decreases with increasing temperature. Relied solder is allowed to increase these characteristics, which will increase the parts rigidity and efficiency. The minimum of mechanical power structures, namely the tensile stretch, Young's modulus, and ductility index, are given in table 7 on the next slide. Next slide, please. Young hardness modulus had a pattern with a relied surface. He also has the highest fragility index. We can see on the figure 8 on this slide. The next slide contains the main conclusions of our work. Based on the obtained values, we can say that the recommended option for strengthening the blades is to create a layer of heat-resistant and wear-resistant material VT-N1 is the wear zone containing of solid parts of tungsten carbide relied titanium bisect solder VBR16 as a binder. Thank you for your attention.
Thank you, Natalia, for your report. Dear colleague, questions? No? I'm not, I haven't any question. It's all clear for me. Thank you.
Thank you.
Dear colleagues, dear participation of the last session today. Before the last presentation, which was provided by me, I would like to say thank you a lot for each participant for present your piece of your research. I hope we will take part of the next conference next year. Thank you a lot, and I wish success in your research. And have a nice rest for the holiday for the summer. Okay, let's begin my presentation. This research was prepared from Lutsk National Technical University in cooperation with Jana Dlugoš University in Częstochowa. The topic, preparation, characterization of a biocomposite base of casein and cellulose. I think nowadays only lazy don't talking which a lot problem we have by using synthetic polymers. And everyday consumption of fossil fuels is increased, and we human beings really have a lot problem in this case. Fossil fuels is still the most important energy resource and raw material widely used with the industry. However, after the immoderate usage of fossil fuels for hundreds of years, the climate change and the environmental pollution issues have become a theater of sustainable development of human beings. Therefore, there is an increasing demand today to replace petroleum-based synthetic material with natural material which are abundant, renewable, sustainable, and inexpensive. One of them, cellulose, is particular, has been used by making for 1,000 years. It's a form of wood or fibers, energy source, building material, furniture, clothing, etc. It has also been exploited as a primary raw material for more than 150 years in paper, packaging, textile, or food industry. In this slide, we can see the structure of wood or plant from tree to cellulose. Cellulose is the most abundant biopolymer on Earth. About 8 multiplied 10 and 10 power tons of cellulose being produced in the biosphere every year. About 50% of the carbon in the biosphere exists in the form of cellulose. It is the main component of plant cell walls, in which produced by photosynthetics. By it can also be synthesized by bacteria or found in animal. The structure of wood from trees to cellulose shown in the first figure in this slide. Due to hydrogen bonds between anhydrocellulose unit, some cellulose chain tightly packaged together and highly ordered cellulose crystal region in the next figure of this slide. Some of crystal and some of amorphous region we can find in the plant or woods, of course. Therefore, for different kinds of structure, domains are found in the cellulose nanometer size crystal region and amorphous region. Please, next slide. in recent years, also research of material derived from renewable natural source has increased significantly. Example of such material are composite biset and gelatin, chitosan, pectin, and casein, which use for matrix. As a result, knowledge about the function characteristic of new material and scope as such natural polymers is constantly improving. Natural polymers such as casein and pectin are potential or hydrogel forming polysaccharides, so they are given special attention because they are biodegradable polymers. An additional advantage of casein is that they have no toxic effects. Modification of the casein structure is the basic for the development of new and improved technological for biodegradable materials. One of the promising areas of this research is the creation of medical films and food packaging. However, solving this problem is not easy because poor casein material have low technological characteristics such as very low strength and elasticity. They are easily soluble in water. Improving the properties can be achieved by obtaining composite material biset of casein reinforced with natural fibers. There are studies develop the development of such materials, in particular the possibility of forming copolymer casein and methyl cellulose and obtain films. Accordingly, the aim our work, the development biodegradable polymer composition base of casein. You can see of this slide the goal task were set. Please, next slide. In this slide, we can see process how we obtain cellulose from plants. We use three different kinds of plants. Both of them is from hemps, and someone is from dew sock hemps. We want to compare which amount we can obtain from these plants, because plants obviously is renewable resource. This process is very easy, it's very known process. We cutting the plants and use solution of trilone in ratio 10:1 and 3 minutes from during the between temperature 100 degrees Celsius facilitate the removal of mineral from resulting cellulose. The process is carried out of heat-resistant flake, mold of flake, heater connected to reflux condenser. After obtaining cellulose, it's the last picture. We use a laboratory homogenizer and after that, the crushed cellulose was filtered through filter paper and then dried from room temperature. Please, next slide. For study of surface, we use optical microscope Leica and microscope for study microstructure. We using scanning electron microscope with EDS microanalysis system for quantity and quality analysis. Please, next slide. We also use FTIR spectrometer Shimatsu, was used to study the chemical characteristic. We try to understand which toxical component include our cellulose and other component. Please, next slide. Impact tests were performed in accordance with current international, very well-known standard, the method Sharpie. For the study, use a Pendium deal. We can see of this slide. The next slide, please. Samples with different percentage of cellulose in the range from 25 to 50% of the mass fraction were prepared for research. Casein glue of the extra brand was chosen and binder. The adhesive is characteristic by high reliability for gluing wooden surface. It has no harmful emission, so it is suitable for production environmentally friendly composite. To prepare the adhesive solution, the powder was gradually powdered into water room with constant stirring. Please, the result mass and leads prepared in the aluminum molds dimension 10 and 10 for 100 millimeters. Please, next slide. Using an EDS adapter, the chemical composition of 3 types of cellulose obtained was studied in the previous slide shows the precision element obtained during the study cellulose. In this slide, thank you. The next slide, we can see the result of one of the piece. According to the research, cellulose contained most carbon, about 55%, and oxygen. Cellulose also contains hydrogen, but due to atomic mass less than 3 of these elements. So it is impossible to defect during the study of the chemical composition. Chemical test results show a small number of elements such as aluminum, bromine, calcium, silicon. Their presence can be explained by contamination resulting from obtained and contact with the holder and with the test samples were placed. The result of the study shows that 3 types of cellulose obtained don't contain harmful elements and heavy metals. Please, next slide. Next. Okay. This slide shows image feature of the same. Different type of filler with degree of filling 50%. To photo clear shows that samples is spectre from ER spectroscopy was used to study chemical composition of the finished samples. The study was conducted to analyze organic compound and determine their structure future. during the test was found that all simplest contain primary aliphatic amides in the range of 1,600 to 1,080 centimeters minus 1 power. Please, next slide. This slide show it should be not that tested simple showed brittle fracture. The result present no dependence in the impact strength in the samples of the type cellulose was observed, but only on the content. According to the result of the study, the impact strength and absorbed impact energy increase almost linearly with increasing the degree of filling to 50 and higher degrees of filling being to decrease. In this feature, we can see a fracture surface of the samples was investigated using the SEM. The photo shows the cellulose fiber lie well on the matrix. There is no pooling of the fibers, and after the impact, there is brittle fracture without sign of plastic deformation in the material. Regardless of the porosity, the material inhibit quite good mechanical properties. Please, next slide. It's the result of measuring the toughness. We can see of this slide the energy G and adsorbed energy and kilojoule per meter quadratic, the toughness. The other samples which include other cellulose content. The most well result have samples which include 50% in the matrix microcellulose. Please, next slide. The impact, excuse me, next slide. Conclusions. The chemical composition of the casein-based composite was also investigated, and results show that general the material does not contain toxic. The impact strength of casein matrix increased to 47 kilojoule meter square for a composition filled with 50% by weights. The increase is due to reinforcement of cellulose fiber with correspond to impact strength of polystyrene, very well known and very used for produce packaging, the other packaging. Therefore, the obtained result confirms the prospect for further research of this material. Accordingly, studies tensile and flexural strengths, thermal conductivity, and biodegradability of the composite will be performed. Thank you for your attention. Last question.
Thank you for your contribution to our conference. I highly appreciate your support and your involvement in this conference. And let me introduce you, present you certificate of appreciation.
Very well. Thank you.
For the amazing session.
Thank you a lot. Okay, this section is closed. Thank you.
Thank you.